Hello class. What we're going to talk about today is a little bit more of application of exponential growth and exponential decay, where these are used in the real world, that kind of thing. All right. Now, just a reminder and a little bit of expansion here. The general format for exponential growth and decay is y equals a times b to the x, where b is the base of your exponential function. All right. And you remember there are two different types, exponential growth and exponential decay. Exponential growth is where it is increasing. That's where something is growing. It's getting bigger and bigger and bigger. And in exponential growth, in our equation, A, that is the initial amount. Or that's the y-intercept, okay? The base, what that is going to be, that is 1 plus r, where r is the rate of growth. So, for example, if something is growing at 5% a year, R would be 0.05, and so B would be 1.05. Right? For exponential decay, this is where it's decreasing. Something is going down in value, or it's rotting, or something like that. We have A equals the initial amount still. Same thing it was with exponential growth. This is where did it start? It started right there at the y-intercept. And this time B is going to be 1 minus the rate, all right, R, which is the rate of decay. So, for example, if it is decreasing by 10% every month, then R would be the 0.10, 0.10. So B would be 1 minus 0.1, so it would be 0.9. All right. So that's that. Let's take a look. We have the value of some car in thousands of dollars. Can be approximated by the model here. Y equals 25 times 0.85 to the t, where t is the number of years since the car was new. What we want to do is first tell whether this model is exponential growth or exponential decay. Then we want to figure out what is the percent increase or decrease. And finally, we want to figure out when would this car be worth. We want to estimate when the car would be worth $8,000. Right? So part A, is this going to be exponential growth or exponential decay? For that, we look at the base of the exponent, which in this case is this 0.85. Right? Well, that is less than 1, so we're going to have exponential decay. Right? Because it's between 0 and 1. So identify the percent increase or decrease. In this case, it'll be decrease since it's decay. And what we do with that, we are going to rewrite this 0.85 as 1 minus 0.15. All right? Because that's what's going to equal this. Remember, the base is 1 minus the rate. So we don't know what that rate is. So 1 minus 0.85 is 0.15. And so our percent decrease is 0.15 or 15%. And that's what we're going to want here because it says percent decrease. So 15%. When will the value of the car be worth $8,000? We're not going to get this exact, but we're going to estimate. And what we're going to do is we're just going to put this in our graphing calculator. And we can use the trace fig function to figure out about when this is going to be $8,000. Remember, y is in thousands, so this is $8,014.43. Right? That's pretty close. So y will be approximately $8,000 after 7 years. Right? So that's not too bad. It's pretty simple stuff. Here's one kind of similar. In 2000, the world population was approximately 6.09 billion people. During the next 13 years, the world's population increased by about 1.18% each year. We want to write the model. Okay, so this time they're giving us information, say you write the equation. And then we want to estimate the world's population in 2005. Then we want to figure out when did the world have $7 billion, or when will the world have $7 billion, depending on how long it takes. All right, so first things first, we need the model here. So we have A, this is growth because we're having more and more people. So A times 1 plus R to the T. our initial amount, A, that's 6.09 billion. We're going to do it in billions. The rate is 1.18%. We've got to write that as a decimal, so this will be 0.0118. So when we plug those in for A and R, we have 6.09 times 1 plus 0.0118. Simplify this, and here's our equation. We want to figure out how many people there were in 2005. Well, 2005 is 5 years after 2000, which is our initial value. So T will be 5, and you just plug that in, type it into your calculator, and you get approximately 6.46 billion people, which is a lot of people. Next question, when will we have 7 billion people? And to do that, again, we're going to use our graphing calculator. Type it into your y equals there, take a look at the table, and that's going to be about 2012, 12 years after 2000, so 2012. In 2012, we will have 7,010,600,000 people. So, well, we did have that according to this model. All right. So what I want you to do is answer these two questions. Pause the video, work them out. You may need to back up to see the stuff on the other pages. That's fine. And then come back and see how you did. Alright, let's see how you did. Number 5, if the car can be value of the car is approximated by this model, how does that change things? And then what if the world's population increased by 1.5% instead of 1.18%? Okay. So for the car, you should have gotten it's a 10% decrease in value, which makes the car worth $8,000 after 10 years. And for number 6, you should have gotten, actually that is a typo right there, so that's not right. Okay, but it still is the year 2009, so let's take a look at this. First, the car. We're just interested in that B. Right, this is our B. That's where we're going to get the rate of increase or decrease. So we plug that in. 0.9 equals 1 minus R. So R equals 0.1. But we have to write it as a percentage. So 10%. And we want to figure out when it's going to be $8,000, which is going to be approximately right there using the trace function on the calculator. So that's what we're looking for, 10.85 years. Okay, so for the world's population, number 6, here's our basic equation. This is growth, so it's A times 1 plus R to the 6. Our initial value is 6.09. Our rate is 15%, so not 15%, 1.5%, so 0.015 plus 1, which is 1.015. That's what you should have gotten right there, not this. It's got an extra 1 on that. All right. When will we have 7 billion people according to this model? Well, 7 billion people is going to be right here sometime during 2009, because we got just over that in 2010. So in 2009, we will have 7 billion people. Or we did have 7 billion people according to this model, which I don't know if that's right or the other one's right. Who knows? Okay. Now let's take a look at this. This is looking at half-lives of radioactive isotopes, which is something that uses exponential growth and decay all the time. It's in science and stuff. So the amount Y in grams of the radioactive isotope chromium-51 remaining after T days is Y equals A times 0.5 raised to the T divided by 28. Where A is the initial amount, however much you started with. What percent of the chromium-51 decays each day? Now, what this doesn't tell you, and just good to know, this T divided by 28, what this is, this means that you're going to have this 0.5, you're going to lose half of the radioactive isotopes every 28 days. All right? So this is a half-life. Radioactive stuff, it decays in half-lives. And so this is saying the half-life is 28 days. We want to know how much it's going to decay each day. So what we do, we break this down, and we separate this exponent out, and this is the 128 times t. And then we take this, stick this in your calculator, and we have a times 0.9755 to the t power. Now we're going to take this and we'll do that 1 minus r thing, figure out what is r. So we're going to rewrite this, and so r equals 0.0245. So this is our rate, which means we are decaying at 2.45% every day. All right, so that after 28 days, it's lost half of its radioactive isotopes. All right. Compound interest. Compound interest is really cool stuff. What this is when you put money into a bank or you invest money and they pay you interest on it. And then next year, they're going to pay you interest on the interest. And then they'll pay you interest on the interest on the interest. And then they'll pay you interest on that interest and that interest and that interest and all of the interest, and it just gets bigger and bigger and bigger and compounds, and it's really nice to get. I wish I had more of it. Now, this is the formula that we use to figure out how much money we will have after so many years. All right? And the way this works, A is the amount you'll have after T years have gone by. P is the principal, that's how much money you started with. R is the annual percentage rate. N is how many times are they going to pay you interest each year? Are they paying it monthly? It's 12. Are they paying it quarterly? That would be 4. If they're paying daily, 365. And then T is how many years are you going to let it sit there in the bank earning interest. All right. So let's take a look at this. You deposit $9,000 in an account, pays 1.46% annual interest, which is huge for a bank account. Find the balance after 3 years if the interest is compounded quarterly. So we're going to take our equation. All right. A is what we're looking for. P is the principal, that's the $9,000. R, that's the interest rate, 1.46%, which we have to write as a decimal, so 0.0146. It's compounded quarterly, 4 quarters in a dollar, 4 quarters in a football game, all of that. Right, so 4 quarters a year, so N is for both of them, and after 3 years. Then we're just going to take this and stick it in our calculator, and we end up with about $9,402.21. So, not bad. $400 after 3 years, just letting it sit there. All right. Now, what I want you to do, I want you to answer these 2 questions here. If you need to back up to get that formula again, that's fine. Pause the video, work these out, then come back and check your answers. All right, you are back. Let's see how you did. All right, percent that the iodine 123 decays each hour, and that will be 5.19%. And if it want the balance after 3 years, if it's compounded daily, so interest rate stays the same, but now we're compounding it daily, you get an extra couple of pennies. It's 9,402.95, 95 cents. So if that's not what you got, let's take a look. So here's our original formula for the isotopes. We split the T and the 1 and the 13. So we split those out. We have 0.5 raised to the 1/13th, which we plug in our calculator, and we get 0.9481 to the T. We take this, and remember B is going to be 1 minus R because it's decay. So we have this. B is the 0.9481 is 1 minus R, so R is 0.0519. And then you take this and rewrite it as a percentage of that. Now the compound interest. Start with a compound interest formula. Plug in what we've got. The only thing that changed here is it's 365 compounding periods, not 4. Everything else is the same. Same interest rate, same principal, same 3 years. And here we get an extra little bit, couple of pennies. All right, more often it's compounded, the more you'll get paid. So that's nice. And that is exponential growth and decay. Hopefully you found that useful, and I will see you next time.